Might as well go ahead and get started. So thanks to all my students who are here. These are soon-to-be A students. So thank you very much for coming. Tom asked me how long this lecture is going to be to infinity. Well, I don't know. Just do 1 over 0 now to your answer, right? Right, Nicholas? Yeah. All right, so to infinity and beyond, and I promise you there's not going to be a lot of math. I'm going to try to explain some of the concepts about infinity, what it means, and how it relates to chaos, okay, what chaos theory is, and then how that relates to what we call fractals. So I'm going to do that in that order. I'm going to start with just a few important people, talk about what infinity is, if I can, okay, and then describe chaos theory, and then get into fractals, okay? So I hope you enjoy it. Now, yes, I mean, that looks chaotic, doesn't it, okay? But I promise you it won't be like that. Okay. Okay. So I want to first introduce you to a few important people because I feel like you should know some of the key folks behind this concept, the concept of infinity, chaos, and fractals. And these are just a few, just a tiny fraction of the folks because really it goes back to ancient times. And we're going to talk about Zeno and things like that, the dialectic, and how they had the ideas of infinity as well. But a few key people I want to bring up, so it's really an introduction, and how they supported the ideas of, especially in what the idea of what infinity was, and how it relates to even can we model real life applications of infinity. Okay, so here we go. We're going to start with Bernhard Riemann. Now, I think some of you may have heard of Riemann before. Riemann didn't live very long. Actually died when he was 39, okay, when he was a sickly child. But he really was one of the first people to talk about geometries. Not just what geometry, what people thought about geometry, like Euclidean geometry. The Euclidean geometry is the geometry that you all study in high school, right? Straight line, 2 points determine a line, and so on and so forth. Well, Riemann took it much further. I mean, to the point where people just didn't understand him at all. And in fact, it really wasn't until Einstein, theory of relativity, that people started to understand really what Riemann was talking about. So Riemann really described in a really important lecture when he was only 26 years old. Can you imagine, 26 years old, about what geometry is and what it really can be. And it's really an amazing thing. And I think some of you guys, remember the movie we saw, the math movie? They talked about Riemann, right? They talked about, and remember that really weird looking clip they had with all these weird geometries? Well, that's just some of the applications that Riemann was talking about. Things way ahead of his time. So, yes, it doesn't necessarily relate to chaos or infinity. Well, it does relate to infinity, but chaos or fractals, but it certainly has its roots with Bernhard Riemann. One of the biggest things he did, one of the most famous things he has is what's called the Riemann hypothesis, which talks about the natures of prime numbers. And if anyone can prove that, you'll be a millionaire and, of course, extremely famous. So actually, he's quite a famous person in mathematics. And many, many mathematicians now are trying to actually prove the Riemann hypothesis. Because if you can prove the Riemann hypothesis, you will basically destroy, okay, all cryptography. Because a lot of cryptography now are based upon prime numbers and for example, RSA, Riemann, Shivas, Adelman, you multiply two large prime numbers together. When you multiply them together, okay, and I give you just the product, okay, it's extremely difficult, especially if the prime numbers are large, to break the code because it's very difficult to factor those two numbers. So anyway, Riemann hypothesis is extremely important, and people are rushing around to prove it, and it's been years and years without any luck. So it's a very famous guy. But unfortunately, he died way too young. Next person, George Cantor. Now this is where it really starts. George Cantor was one of these people that was completely comfortable with the idea of infinity. Because, really, the idea of infinity, what's it really mean? We think of infinity really just to mean something that's boundless, okay? And calculus, for a lot of things, are based upon infinity, right? Limits, so on and so forth. So for your Chinese, Weiji Fen, okay, calculus. You really need to understand sort of the idea of boundlessness to understand, limits and how derivatives work. So in this case, Cantor was really Cantor was really at ease at discovering what infinity was and talked deeply about it. One of the things he did was he talked about a one-to-one correspondence, because he said, is there just something that's boundless, or is there something more than that? In other words, is there just one infinity or many infinities? It's really important, right? I mean, what does it just mean to be boundless? It's not good enough. So he angered a lot of mathematicians because he really upset the apple cart, as they say. But one of the things he did, he established a one-to-one correspondence between members of two sets, defined infinitive and well-ordered sets. And here's the key. He proved that real numbers, now real numbers for your non-mathematicians, it sounds kind of goofy. What's a real number? What's a fake number? Real number? No. A real number are numbers that you guys, everyone here understands. Like 1, 2, 3.5, pi, right? 1/3, like what's 1/3? You know, 0.3333 repeating. 1/7, okay, it's a fraction. But you get like square root of 2. Square root of 2 is a decimal number that keeps repeating. That doesn't repeat at all. It just keeps going on forever. Okay, so these are all real numbers. Now, integer numbers, okay, are just the numbers that we all learn as a child. You know, 1, 2, 3, 4, and so on and so forth. And he proved that real numbers are actually more numerous, okay, than integer numbers. Okay, and that's a big idea. So he showed there actually are at least two infinities. Of course, there are more, but that's what he showed. Okay, and he relates to something called the continuum hypothesis. Okay, so I'll get to that. I'll come back to that a little bit later. David Hilbert, again, I like his hat, right? I wouldn't be caught dead wearing that hat now, but anyways, he's in Germany. Okay, he explains it. Okay, preeminent mathematician of the late 19th century and early 20th century. Okay. Now, he is famous for proposing the 23 famous problems. Occurred now, the 8th, remember I talked about the Riemann hypothesis. So he talked about that. Another thing, one of his famous problems that he said, unsolved problems, was the continuum hypothesis, which Cantor talked about, and I will briefly mention about the continuum hypothesis. So Hilbert was just one of these people that just, he had a broad range of ideas. He brought these all together, and he sort of solidified mathematics. Because if you look at this date when he was alive, he died. He died actually in Germany during the Nazi occupation. So it's very sad. In fact, all the mathematicians had basically left Germany at that time. Most of them went to MIT and Princeton and so forth. They went to America. Actually, the World War II was very good, in a sense, for mathematics in America, because all the top mathematicians in Germany and other places went to America, okay? Went to Princeton and so on. But David Hilbert stayed around, okay? Now, here we get now to more of the 19th century, Alan Turing. Now, have anyone here heard of Alan Turing? Ah, we got one. Nicholas certainly has. Robert. Alan Turing. Really tragic story, okay? But anyway, I won't get into the story, it's a long one. But he was instrumental in breaking the German Enigma codes. In fact, really considered one of the fathers of modern computer science, along with John von Neumann and other people. But here's the thing. After the Second World War, he talked about the chemical basis of morphogenesis. And this was really, in a sense, the start of the idea of a deterministic randomness or chaos theory. And really what chemical basis of morphogenesis talks about, he talks about, is there a way that we can describe non-uniformity seen in animals? Like, have you guys seen the black and white cows, the Holsteins, right? You ever wondered how those black and white strips kind of match up? Why each cow is different? We look at the cats outside, right? They got stripes on them, right? They don't all look the same. And really, how has that come about? I mean, what about galaxy spirals and so on and so forth? Okay, so he tried to have an idea that maybe small things join together, small processes, small systems. When they join together, they create complex shapes, or even simple shapes that we see today. Things that we don't know how it works, but it's just through simple processes that creates what we see today. And that's really what it is. It's a groundbreaking paper, and it's free on the internet. You can read it, no problem. So Alan Turing, I mean, it's one of his ideas, but he did a lot of other things, especially with computer science. But really, he basically started, in my opinion, the idea of chaos theory, deterministic randomness. Okay, and we're going to keep coming back to that theme, okay? And I promise you this is going to lead towards fractals, okay? And chaos. All right. Finally, Mandelbrot. You can't miss Mandelbrot, okay? Benoit Mandelbrot, okay? Polish Jew who came to America, I forget now, just after the Second World War. He worked at IBM, and he discovered what we now know as the Mandelbrot set. And I will show you some pictures of the Mandelbrot set a little later, okay? It's just beautiful. And in fact, at the end of this class, okay, I will show you actually a three-dimensional Mandelbrot set, and it's like a little movie, so I hope you enjoy that. But here's what he did. He laid out the theory of roughness. That's interesting, right? He said, you know, how long is the coastline of England? You know, you can't really measure it, right? It's random. I mean, you can't make a straight line, and you're sitting there measuring all the time. You can't do that, right? So he came up with the idea of, you know, fractal dimensions. And basically along with this, he talked about, you know, it's not just the jagged coastline of Britain or any coastline, but what about mountains? How are mountains created? Or is there a way we can make sense of how the randomness we see in mountains, okay? River branching. I mean, our veins. You ever looked at your veins? I mean, they look very similar to rivers, right? Maybe it can explain some of these things. And it led to a huge revolution in the idea of nature, okay? Of understanding nature with mathematics. So he's critically important, and again, he was probably the first person to actually employ computer graphics. Okay, I think 1979 or something like that, he came up with the Mandelbrot set, which I'll show you later, and the rest is history. Okay, so critically important. All right, so that's it from the folks, the introduction. Okay, now we're going to look at infinity. Ooh, infinity, there it is. That symbol, kind of the 8 on its side, okay? It's, I think the Indonesians, they do half infinity, but this is a typical shape, you know, it just means it goes on forever, okay? And that requires infinity, okay? So the concept of infinity, actually, as I mentioned at the beginning, really has been around for a long time. So, since ancient times, people have talked about infinity, okay? You know, the idea of it's just something bounded. I mean, even when you're a kid, you ever thought about that? You know, where is it end? Where does something end? You look in the sky, you know, how far does it go? It's just a basic thing, right? Basic idea. I think everyone here has experienced that. But Zeno, I mean, it's not just Zeno, but I'm going to focus on Zeno. He thought about it. He had famous thought experiments, and he came up with paradoxes. And, excuse me, one of his famous ones was the Achilles versus the tortoise paradox. And really what it means is that, you know, obviously the turtle is a slower runner, right? And you got Achilles here. And as long as you give the turtle a head start, understand? So the turtle starts, okay? And then Achilles starts running. By the time he reaches where the turtle started from, right? The turtle has already moved ahead, understand? Okay? And at that point, okay, he goes from there, he goes to where the turtle is, right? But by that time, the turtle's moved ahead again, right? And then again, he starts here, he goes to where the turtle was, by that time the turtle's ahead. You understand? So what Zeno says, hey, it doesn't matter how the fast runner is, he's never going to catch the turtle. Okay, that's his paradox. Okay? So it's just an idea, it's a concept that shows that people were thinking about ideas of infinity. Can we play with the ideas? And it's critical. Greeks were just master thinkers, okay? And this is just one of the ideas. So again, this is certainly not probably the first ideas. People have thought about these for years and years, but hey, it's something that we can verify it happened in Greece. And you know, Zeno was definitely one of the masters at this, okay? All right. Concept of zero. Now, okay, I promise you this infinity part is probably the most boring part of this lecture, okay? It gets more exciting in a minute, trust me. I have a lot more pictures for you, okay? No problem. Thing is, zero. Why is zero critical? Now, everyone here knows the numbers, right? Just the basic numbers. 0, 1, 2, 3, blah, blah, blah. Oh, nicely. Go to sleep, right? But zero really didn't exist as a number for a long time, okay? Now, you guys know this, right, in those movies, yes? Okay? 0 didn't actually exist. Okay? You had an idea of 1, 2. In fact, even negative numbers didn't make sense. Okay? But, you know, it really, two cultures, independently as I understand, developed the idea of 0. Mayan culture, believe it or not. Okay? Mayan culture. Incredible, actually. And the Indian culture. And it's really theorized the Indians developed the number, given that their major religion values nothingness, okay? And they embrace the idea of the void. So there's actually a temple that actually has 0 carved into it, okay, inside. So it's very fascinating. So they're the first to use 0. And so what it means is, see, cultures before the Indians, okay, where there was 0, nothingness, they just left things blank. They didn't put a number. But the Indians were first to put a 0 in place of where there should be nothing, right? And that changed everything, okay? And this is where it relates to the infinity, because these are some of the questions that people were asking themselves. 1 over 0, does it equal infinity? If that's the case, 1 over infinity, does it equal 0? Does 0 times infinity equal 1? I mean, no, there's some problems, right? They had some problems right away. Say, Brahmagupta has a whole list of problems he talks about. And once you have 0, he can think, well, you know what? You see, if I owe Nicholas, for example, money, say if I owed him 10 renminbi, okay? Then I have negative 10 renminbi. It's like a debt. So the Indians really talked about, you know, debts and, debts in surplus, okay? So that's where the idea of negative numbers come around, and you use 0 as that pivot, okay? So with 0, this idea of infinity started, it came up in mathematics, so that means now that mathematics turned from just a practical application to a theoretical one. Understand? It's a really interesting turning point in mathematics. So it went from a practical one to a theoretical one. Okay, well, this is not how we understand 0, infinity. One of the best ways to understand infinity is just use limit. Okay? You got to take limit from the right, limit from the left of 0. Think of it as it goes to 1 over x. And you can approach something we call positive infinity, the sign. And as limit is x approaches 0 from the left, 1 over x gives you negative infinity. So we really don't have a definition of 1 over 0. It doesn't make any sense. Okay? That's why we say it is undefined. Okay? Because it really is. So the limit is really important, crucial to calculus. So that's really more how to understand that. Okay. So I won't spend too much time here, but again, infinity really has not been without dispute. People have talked about this over and over again. I mean, look at Zeno's paradox, right? Does that really make sense in real life? I mean, no, right? Because you can easily have a faster runner will overtake a slower runner. So people have talked about these all the time. Really, it was just a thought experiment, okay? But it's been disputed. And that's why George Cantor, remember, beginning, he's the one that really solidified what infinity is, okay? Or what we understand it to be. Okay, again, it's not a number. It's really more of a concept, the idea. And this is, again, infinity is important to understand why fractals, okay, are as they are, because they're infinite in a sense, okay? The smaller you look at something, you're going to see the whole part, okay? That's why infinity is really important to understand what fractals are. And we use infinity all the time. Meaning pi, it goes on forever. Here, we often take sums, infinite sums. This here is the Taylor series, okay? Expanded around some value a, okay? And that starts leading to ideas here, okay? So people start talking about it, trying to decide what do we really mean. Remember, infinity is not a number, it's a concept, okay? Okay, countability. So I promise you, we're moving on here. We're going to get into chaos theory in a moment. Countability. Can we count things? Remember I talked about Cantor briefly? Cantor, again, showed, as I mentioned earlier, showed the size of real numbers are greater than the size of the natural numbers. Okay? And this is what you see here. This is what the continuum hypothesis means. There are no infinities between the size of natural numbers and the size of real numbers. And in fact, Paul Cohen, okay, an American mathematician, showed that it cannot be proved using just the axioms of set theory. In fact, it makes it undecidable. Okay? So we really don't know using the set of axioms. So what they only know is either natural number size of infinity or the real number size. So you've got these kind of weird thing. You got two different infinities, okay? One for the size of natural numbers, one for the size of real numbers. And is there a continuum? Well, Paul Cohen proved that it's undecidable. We don't really know, because you can't decide it on set theory. And by the way, set theory is the theory in which mathematics is based on. I think I mentioned this in class, right? Okay. Now, this is an example of a diagram that this is kind of one of the things, these diagrams, that, you know, every mathematician wished they proved, okay? This diagram shows that the size, infinite sets of rational numbers, and again, for you non-mathematicians, a rational number doesn't mean a logical number, okay? A rational number means ratio of integers, okay? Like 1/5, 2/3, 5 even, because it's 5/1, okay? That's a rational number, okay? So he showed that the size of the rational numbers and the natural numbers are the same. So again, he's taken infinity and crystallizing it in his hands, okay? And what he's done is he's taken all the rational numbers, start with 1, so 1/1, 1/2, 1/3, all the way to infinity. Then he does 2/1, 2/2, well 2/2 is just 1, right? 3 at 2/3, 2/4, well 2/4 is just a half, 2/5, all the way to infinity. And he does it this way as well. So you got this sort of this infinite square, or block if you want to call it like that. And you see these arrows. So he draws an arrow from 1/1 down to 2/1, up to 1/2, across to 1/3, down to 2/2, down to 3/1. You can follow these arrows. You see this? How it follows? Okay? And if you were to take that and stretch it out, okay? Just imagine. It's like coiled up, right? Coiled this way for you guys. Just stretch it out. There's a 1-to-1 correspondence between the rational numbers and the natural numbers. And in fact, this proof is on his grave. Okay, it's very interesting. So that was one of the most amazing proofs to show that these infinities are actually the same. Okay? And there's also another proof, really a counter proof, to show that the real numbers are much bigger than the natural size numbers. Okay? Now, does it just relate to numbers? No, now we're going to talk about shapes. There are one-sided infinite shapes. Okay. Mobius strip. Anyone heard of a Mobius strip? Okay, I have one here. Mobius strip. Okay, so everyone see this? Can everyone see this arrow there? It's a little bit kind of a weak arrow. Can anyone see that? Okay, this is a one-sided shape. Okay? So, for example, so watch. I'm going to see, I don't know if I can see you guys. So here's the arrow, right? So what I'm going to do is I'm going to walk it back. And I'm not going to flip it. I'm not going to turn it over, okay? So if I walk it, right? Watch what happens. See the arrow, everyone? Again? So if I walk it, right? Now, let's see if I can do it this way. Maybe I can do it this way so I can see it. So I'm going to walk it, right? I'm not going to flip it. Watch what happens. Just watch what happens. I'm transversing the whole part. I come back. See that? I never flipped it. I didn't turn it over. Okay? Do it once more. Here we go. This is not a magic trick. I didn't flip it. Okay? But I just I'm walking, right? Walk up, he's back, right? It's a Mobius strip. Okay? And in fact, it shows right here, this is a famous picture of the ants walking the Mobius strip. And I was kidding with Nicholas yesterday. It'd be nice to get an ant and just put him on here and let him walk, you know? Do you ever go anywhere, you know? But, I mean, yeah, so it's an example. So this is really infinite length, but you just keep going over and around and around and around and around, right? You just keep going and going and going. You these ants will transverse both sides without going over the edge. Okay? Now, interestingly, here's the Klein bottle. Anyone heard of Klein bottles? Yeah. They're actually, it's a two-dimensional representation. Okay? And I know it looks like it's going in, but actually, you know, some topology will tell you that actually there's really no interaction between those points. But actually, if you follow along, if you climb around here, go in, you don't go in here, and you're inside now. Okay? You go inside, and you come out, and you transverse. If you just sit there and try to imagine tracing out, you can actually go in a circle. And you actually transverse the outside and the inside. Okay, so if you just walk it. If you walk it, say, walk it around, you go in here, you're not going to touch the points. Now you're inside, right? Now you're inside, 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 inside. Ah, now you're outside. Okay? So that's one of the amazing things about a Klein bottle. Okay? And actually, people make these things. You can buy them on the internet. It's really incredible. Okay? So, yeah. So that's my Mobius strip. Now, there's also, yes?
Didn't Escher have drawings that did that way before Mobius actually showed his
I don't know.
representation?
Perhaps.
The
Yeah.
Escher, the Escher strips? The Escher,
Yeah. Escher drawings, but I will bring up some Escher drawings as well in a minute. And some guy made a Klein bottle house. Tom, can you sell these?
Maybe.
I mean, it's interesting, right? I mean, McBride, Charles Ryan made a Klein bottle house. Now, this is just the outside, one of the outside pictures, but actually there are pictures of it inside pictures. So yeah, you can live in a Klein bottle. Okay, so it's really interesting that people have stuff like this. I'm not sure where it is, but it looks like somewhere in the U.S. Really incredible. Okay, and talk about Escher. Bob, here we are. This is actually a Volkswagen commercial, and this was based upon the work Relativity by M.C. Escher in 1953. And again, how does this relate to infinity? Well, it really relates to that you can keep walking around the circle forever. Okay, it talks about different geometries. Remember from Riemann? Okay, Riemann talked about what geometry is, what it can be. Okay, so these are just sort of all things. And what's amazing is you see these guys walking this way, right? But the guy's over here. Okay, so gravity doesn't mean anything, right? And it's incredible that guy's working on a car here, yet there's a car over here and there's a car there. Okay, so if you can step up here, and you can go over here, you can step down over here, walk over here, walk down these steps, and go over here. Kind of cool, right? We should make a building like this, a school building. So it's just it's in art as well. So people like these kind of things, right? I love these. There's one too of a castle where guys are marching around the castle, going up and down stairs. It looks like they're always going down the stairs, but they never go down the stairs. It's very interesting. So, just different things. And again, these are inspired by the idea of infinity, and also by the idea of geometries and what geometry can be. And it's really, in my opinion, it's inspired by Riemann, ultimately. Okay, now we're going to move into something very predictable, chaos. That's a little bit more chaotic, but maybe not. Okay, chaos. And what do you think of when you think of chaos? I mean, you think of, oh man, a storm went through it, right? Or floods, tornadoes, whatever. You think of just things just completely disordered, right? Well, in mathematics, that's not really what chaos means. Chaos really is a theory about disorder. But it really means that small initial conditions, okay, iteratively done, will create unpredictable outcomes. That's really what it means. It doesn't mean, we just can't figure it out. It's too complex. Doesn't mean that, okay? Really, there's two different things. Linear systems, small changes to initial conditions can give small but general predictable outcomes. I mean, a basic mathematical equation, like y equals 2x plus 1. You give me an x, you got a y, right? But in a chaotic system, because it's iterative, okay, means iterative means you're putting in a condition, you're putting it through the system, and taking that output, putting it back into the system, and then putting it back into the system, understand, many, many times, okay? By the time you're done, okay, it's completely different. And if you were to change that initial condition just a little bit, it would produce another outcome that's completely different. Understand? That you cannot predict. So, in other words, if I gave you an initial condition and said, okay, what's the outcome look like? You wouldn't know. You'd have to actually iterate it, okay? And so this is really what chaos theory is about, and applications of, okay? So it's really two different things, as we're going to look at some chaos and some ideas of what chaos theory is. Okay, now chaos theory studies the behavior of dynamical systems, and as I mentioned earlier, highly sensitive to initial conditions. Everyone's heard of the butterfly effect, okay? The butterfly can flap its wings anywhere, Brazil, cause a tornado in Kansas. Well, maybe that's not really, that happens all the time. But, but I mean, in other words, a small condition somewhere can create perhaps some other unpredictable condition. For example, you say, well, why did this tornado happen in Kansas? Well, beyond it happens every summer. I don't know. I mean, you can't relate it back to the butterfly flapped its wings, you know? That's just the idea, right? That sometimes these unpredictable outcomes, you don't know why it happened. It's complex, okay? Like, this is why weather is extremely hard to predict. You ever notice on your weather app, right? On your iPhone or whatever, and you see the temperature for today, and then in about a couple hours it changes again. Why can't they get it right? It's just, it's chaotic. Okay? It's a very complex system. Okay? But here's the thing. Deterministic randomness, okay? And that really is chaos theory. Okay? Deterministic randomness, okay? So it's not just something's too complex, okay? That's not what it really means. Deterministic factors, non-linear relationships that can cause things to look random, okay? And what people try to do is they try to come up with models, okay, mathematical models that could model real life systems that are also complex, and can we do a one-to-one? I mean, can we, if we model this and get a certain outcome, will that happen in real life? Maybe, maybe not, okay? This is an example, a small example. I have the next page of a bifurcation diagram, and it's kind of hard to see, unfortunately, on this here. It's easy to see on my computer here, but if you look at this carefully, this logistics map, you see how it goes? Nice line right here. Can everyone see that? Maybe not. Okay, right at about 3, it splits. Anyone see that? Sort of looks like a little parabola, kind of on its side. Then at about 3.4 or something, it splits again. Now you got 4. And then very quickly, it goes to 8, 16. It really splits. And then in a flash of a second, you've got chaos. So I'm going to show you just a basic diagram of dots, okay, to make this more clear. So it's just an example. And look, it's a very simple thing. And that's another thing. To model complex or chaotic systems, it's very often a very simple equation. Okay, it's not like these huge, nasty equations. Very simple. And they're just iterated over and over again. Okay? So let me just give you an example. Let me show you here. Here's the same function, logistics function, and let me just explain it. Okay, this is about as mathematical as I'm going to get today. But p to the n plus 1. So that means this is an iterative function. So p to the n. So for example, if I have my first initial value put in, that's p1, okay? And p1, what we do is you multiply it by some r, and we're going to start off with 2, multiply by that p1, and then multiply that by 1 minus p1, and that's going to give me p2, right? p3 would just be r p2 times 1 minus p2, understand? And we just keep doing that over and over again to a certain time. Okay, so this graph here, what I said is I said p1 is 0.98. See that? 0.98. Maybe you can, I don't know if you guys can see that or not down here. And this one here, we're going to choose r equals 2. Alright? So when r equals 2, look what happens. I mean, it sort of comes right up, boom, boom, boom. It stops here at 0.5. And every time I iterate it, okay, it just stays at the same level. Doesn't change, okay? It's just a one-time deal. So that, very boring. Just line forever, okay? I can iterate it forever, and it's always going to be at 0.5, okay? Now look what happens when I say r equals 3, okay? Same initial condition, 0.98, but now I'm going to put in r equals 3. So look what happens. Boom, 2. It splits. So, I mean, it stabilizes a little bit. It's like kind of like if you cut a horn in half, right? Trumpet. It splits, but it bifurcates, okay? And it just follows these patterns forever, okay? It's always at a period of 2. Just goes this one, then this one. This one, then this one. Okay, that's what it does. It's amazing, right? It just kind of splits 2. Okay? Now, look what happens when I do r equals 3.5. Same initial condition, r equals 3.5. Look what happens. Got 4, right? Okay? Just goes back and forth, the 4. I mean, it's really amazing, right? A simple function can give me this. Now, it's not chaotic, right? It's still, we can predict it, yes? Now, look what happens when I put r equals 4 in. Watch. It's chaotic. And this is just putting in 4. Look. Again, P1, 0.98. R is 4. And look what happens. I get absolutely no predictability here. Just like that. I didn't do much, right? So I, go from 1, right? R equals 2. R equals 3. R equals 3.5. And then finally, R equals 4. It's amazing, right? Just a simple function can give this idea of randomness. Okay? And that's it. It's nothing complex. This is not a complex function, right? It's easy, right? But look what happens, okay? When you iterate, you get this chaotic pattern. Okay. So now, usage of chaos theory. I mean, this is all nice, right? But what can we really use chaos theory for? I don't have much time necessarily to go through all these things. But really, one of the first things, Turing's original idea, simulation of biological systems. Actually, Dr. Levy, in the 70s, I believe, also tried to do this and found out the hard way that chaos theory really is true. Okay? But Turing's idea, again, maybe how shells have their different designs. Why cows have their designs, yes? And how different animals, okay? This, is an idea that perhaps it's because of how proteins, etc., bind together. And by those proteins binding together through chaos, okay, create these overall patterns that we see, right? We just don't know. I mean, it's like, again, this small initial condition that we see, right? And we iterate it, we get this really weird outcome. That if we saw that outcome, we wouldn't know where it started from, understand? Same thing. We see the cows with black and white patterns. How'd that happen? Well, it's a little bit more complex, right? You've got to come back up. But what he's saying is the morphogenesis, chemical basis of morphogenesis is saying that those patterns probably come from simple biological systems. And it's those those simple biological systems put together create the patterns that we see. Okay, and that was sort of the idea. Now, if you can get mathematical models to simulate these things, perhaps we can do simulation of weather patterns. I mean, Bob, right? There's lots of weather pattern mathematical models, right? Many, okay? Based on chaos, okay? Bird flight patterns. I mean, look at this picture. It's amazing, isn't it? It's hard to see, perhaps, but you can see how these birds all go together and these amazing looking shapes. I mean, can you predict where the birds are going to be in a few seconds? You can't. See it? You know what I'm saying? But individually, birds, relatively simple, right? It's how they interact, and you get thousands and thousands of birds interacting to create these amazing patterns that we would have no idea how to predict, right? Do you see what I'm saying? You take the simple idea of the birds and how they interact, and by putting thousands of them together, you create these amazing patterns. Like a school of fish, right? Fish seem pretty stupid, right? But they're not, okay? But but if you've been to the tropics, you see how they move together? It's like on a flash, right? How does that work? It's incredible, isn't it? So that's what we're talking about here. Stock exchange. Ooh. Predict the stock market. People have been working on that for a long time. Now, if you can predict the stock market, you'll be rich for about 2 days. Then when the stock market crashes, because everyone else will be doing the same thing, it'll be a problem, right? But I mean, it's chaotic, right? You can't predict the stock market as far as we know, anyways. Maybe. If you know, let me know. Talk to me afterwards, okay? You can predict the stock market. But really, right? It's a thing to think about. Population growth, spread of epidemics, and so on and so forth. I mean, there's many applications. Fractal file compression. There's a good tongue twister for you. Can be theoretically up to 600 to 1. Wow, that's amazing. Here's a cool thing, especially with computer graphics. We can create computer-generated graphics like movies and games. And this is going to lead now to fractals, okay? Because fractals are based on chaotic systems. And like clouds, landscapes are fractals according to Mandelbrot. In fact, when he was talking about the length of the coastline of England, he was also referring to, hey, how is a mountain? Is there a way we can sort of predict what a mountain looks like, or can we make some sense out of it mathematically? Okay? And that's where the idea of fractals come in. Okay? So with computer graphics, it's excellent because you just need a small initial condition, iterate it, and you got a mountain. Okay, now I'll show you just a quick little thing how to do that. Okay, it's pretty interesting. Okay, here we are, fractals. Okay, it's a beautiful looking fractal. Okay, now Mandelbrot coined the term fractals. Okay, Benoit Mandelbrot. Okay, but it really starts actually with Cantor. Remember George Cantor? Oh, we didn't forget. Okay, he was challenged to get a set that had infinite points. Okay, understand? Yet a length of 0. Understand? So can you have a set of numbers that has infinite points but yet length of 0? It seems kind of weird, right? And he said, no problem. And here's how he did it. So for example, suppose you had 0 here and you had 1 here. Now, if you think about it, just a little bit of a quick math lesson. In the real number line, right, between 0 and 1, how many numbers are there? There's infinite numbers, right? It's real numbers, okay? I mean, if you don't believe it, you give me a number which you think is the end, I'll give you another number, okay? Just keep adding a decimal to the end, okay? It's easy to prove, okay? So what he did is he said, hey, look, I'm going to take this set, 0 to 1, and I'm going to take out the middle third. Okay? So now you have 1/3 here left and 1/3 here left, right? So you got 2/3 left, 1/3. Now, look, how many points? Well, you really have an infinite number of points, but you're really starting out with 0 and 1, right? But just look at the end points of the line. You got 0, okay? You got a third, 2/3, and you got a 1 here, right? So you're actually increasing the number of points, right? But you're making the length a third less, yes? And do it again. So he did it again. And each point, you can see he takes a third out of here, a third out of here. Do it again. Third out of here, third out of here, okay, here, and here. You see what he's doing? You do this over and over again. You take this to infinity, right? What ends up happening? Well, remember, you're going to infinity, yes? Means on forever. What you're going to end up with is an infinite set of points, but there's going to be no distance, there's going to be no length between those points if you take it to infinity. Okay? And that was his point. Now what's really interesting about this is actually it's like a baby fractal. Because look, I'm going to be talking about what a fractal is, but let me just start with it. Fractal really is something that's self-similar. In other words, when you look at a small part of the fractal, right, you see the whole set. Okay? That's what really a fractal means. So you look at this whole thing here, you take part of it, yes? Doesn't that look like this? Maybe shrunk? And look at this little part. See? If you were to expand this out, it would look kind of like this, right? Now, we stop it here, but you imagine it going on forever, right, to infinity. You take a small set even here. Okay? You can see the whole set. So this really is a fractal. It's the start of the fractals, okay? And I'm going to describe what a fractal is next. But it started with Cantor. And you see, this is why infinity is important, okay? Because you're taking it to infinitum, okay? Going forever, all right? Now, here's a fractal. Okay. Fragmented geometric shape that can be split into parts, okay? And really is a reduced copy of the whole. A property called self-similarity, okay? So, what they're saying is, you look at a part of it, right? And you see the whole thing. You ever hear the saying, if you look into a grain of the sand, you see the whole universe? That's kind of the idea, right? That you look at a small part, you see the whole picture. Now look at this thing here. Here's an example of chaos. You got this triangle that starts off, see? And you do one iteration. See the iteration? You do it over and over again, and look what you end up with. You end up with a mountain that's completely, you would never have an idea how it started, right? I mean, look at this thing. As it gets complex, it becomes a small looking, mountain looking shape, right? You cannot determine what it initially looked like, okay? So this is where the ideas of fractals come in. Now this here is the Mandelbrot set, the part of it, the overall view of it, okay? And again, just to talk about self-similarity, I'm going to show you some pictures and I'm going to point out some self-similarity things. But, for example, see this little bulb here? We call it a little bulb. Well, that little bulb, if you look here, you see it here as well, right? And if you look at the top here, you see this bulb? It looks like the whole bulb, right? Okay? So it's just an idea of self-similarity. And these, again, this is a Mandelbrot. This is a set that that Benoit Mandelbrot did a computer graphics of in 1979. Not of this quality. Okay, this is done by Wolfram. Okay, a Mathematica, but not my picture. But it's certainly an example of what the beauty of fractals. Okay, and again, as I mentioned, what are fractals? Well, self-similarity. We talk about clouds, right? I mean, not exactly, but you know, clouds are one. Mountains, ranges, craters, veins in your hand, rivers, you know what I mean? So you see these everywhere. Okay, now let's look at some ones in nature. Look at this. I mean, this is a desert floor. I mean, it's amazing, right? These cracks, how they're spreading like this. It gives you a sort of a fractal idea of, you know, of these little irregular shapes, and they make up a whole floor. This is just this is not obviously not real, but it's a tree. Now, remember we were talking about self-similarity? Well, look at this. You see how this tree, look at this whole tree, right? Now look at the tree on the side, the branches. Doesn't look like the whole tree? Okay? And look at this thing right here. Looks like the whole tree, right? Now, this is the actual tree. Now, this tree, excuse me, are you looking at the whole tree or just the branch? See what I'm saying? You don't really know. And now I can tell by this little thing here, you're probably looking at the branch. What I'm saying is, it just shows you that, you know, maybe you're looking at the branch, maybe you're looking at the whole tree. Okay, so it's an idea of fractal. So this branch here, if you're going to take this rest away, and you're going to take the picture and tilt it like this, maybe you think, hey, we're taking a picture of a tree and a bush. You don't know, right? You don't know it's a branch. This is the idea of fractal. So you see these things in nature. This is actually particularly amazing. It's broccoli. I've never seen this broccoli. Have anyone eaten this? It's really cool looking. But it's a wonderful fractal, because if you look at these little bulbs, it looks like the whole vegetable in one shot, right? I've never eaten these things. It looks kind of creepy to eat, to me, honestly. But anyway, it shows you it's a really nice looking fractal, actually pure fractal in nature. Okay? So these are just a few examples. I mean, there's many, many, many examples I can go through. Okay? All right. Fractals in art. Okay, Escher, Bob had mentioned this earlier, okay, that, you know, art uses a lot of fractals, especially people like Escher. Escher was amazing, from Holland, I believe, and he was a master at tiling of the plane. So he had all these different shapes, and he put them together. You can see these little lizards, they all sort of join together, these black lizards and white lizards, and how they all meet up, okay? And he tiled the plane, and it just goes towards infinity in the middle, okay? But these lizards, there's no spaces. They all join together. Okay, see how their feet join in with the other feet? Okay? It's like complete tiling of the plane, okay? It'd be great to have a floor. Like, we'll make the hall big floor like that. Would be cool, wouldn't it? Big mat, you know? Get the guys to do the stone pieces and make one of these. That'd be a lot of work, wouldn't it? But it's just an example. It's in art as well. Okay? Escher, if you don't know about M.C. Escher, go on the internet, research about M.C. Escher, and you'll just be amazed at some of the stuff that guy drew. It's incredible. Okay, now, Hilbert. Remember Hilbert? So he had some ideas as well. Hilbert curve. This is just an idea that he says, hey, if you took the letter U, right, and you iterated it in such a way, you can create this kind of weird looking pattern. Okay? Nothing really special, but it's just an example of taking a small thing, small character if you want to say, and creating a complex shape. I mean, it's more complex. It's not too complex, obviously, but it's interesting how you can take these and join them together, right? And it's a fractal dimension of 2. Doesn't increase the width, just goes kind of lengthwise, all right? And what someone else also did is 3-dimensional Hilbert cubes. Cool. We need one of these, don't we? And then we need one of these guys. Who wants to make one? Anyone? Sean? All right. But this one's an interesting picture. It's really unfortunate. It looks like the guy took like tailpipes or something and sort of joined them together, but they're all rusting. I mean, I feel bad for it. I mean, it's great. What an awesome thing. And this is a Hilbert cube at some museum, but it's like three-dimensional. So you can see these things sort of loop around each other, right? Like this. Okay? Because Hilbert talked about different spaces, not just what we see as space, but he talked about different spaces, which allowed for different fractal dimensions. So, you know, Hilbert also, his groundwork, mathematical groundwork, allowed for some of these things to take place. Okay? So just some interesting examples. Okay. Now here's one that's another two-dimensional one. The Koch. Some people call them Coke, but I call them Koch. Okay. Koch snowflake. It starts off with an equilateral triangle. An equilateral triangle is a triangle with the same length of sides. Okay. So this side is the same as the length of these two sides. Okay. Well, this side, plus this side are all the same length. 60 degrees each angle. And what you do is, you start up an iteration. Just like the mountains, remember the mountain we just did, like I showed you? We're going to do the same thing. But when you have the side of the triangle, what you're going to do is you're going to split it here. And you're going to put a point on, okay? So you're going to make it, you're going to point each side. And you do it over and over again. See how it does it? Right here, see? Boom. Sort of points out. That gives it, you give it horns, okay? And each side. Each side, you put in like a little point, okay? So you're actually increasing the length. Do you understand? The perimeter, okay? The perimeter is the length of all sides, okay? The sum of the length of all sides. And when you do this perimeter, you keep doing this over and over again, you get an infinite perimeter, yet finite area. Now that's amazing to think about, right? Just like with Cantor's set, no length, but yet infinite points. Well, this thing is kind of also weird. You take this to infinity, you have infinite length perimeter, but yet finite area. Okay, so that's pretty weird. Okay, so it's just an example of a basic fractal. And in fact, I think a lot of times in high school, I don't know if you did in high school or not, but we did this as a kind of a group work project. You draw a few iterations of the Koch snowflake. Now, the one I like a lot is the Sierpinski triangle. And these ones are the ones I rendered personally. Okay, so I have a mathematical package that I render these things. And you may not be able to see it from there. I hope you can. But direct your eyes to these dots here. 1, 2, 3, and then you got these dots here. See that? So what we're going to do is, if you can imagine drawing a triangle, imaginary triangle from these two. You see these points here? And then from here down, you see that? And then from over here, see that? Now, what's left? What did I leave out? I left out the inverted triangle in the middle. See that? So what I'm going to do is I'm going to take each triangle and add another dot in midway between each side. Okay? But I will not do that for the inverted triangle. Okay? Understand? So in the next iteration, I'm going to have a dot here, here, and here. I mean, it is on the inverted triangle, but you'll see later I won't be using it again. Okay? And then same thing here. Here I'm going to put a dot here, here, and here. And then this triangle here, I'm going to put a dot here, here, and here. So watch this iteration. Not very exciting, right? But I've done it. And is there a fractal? Well, you can look at it, right? Because now, you see this here? This is what I originally had, right? If I go back, see this? 6 points. Well, if I go here, I've got them right here, right? And I've got them right here, see? And then right here. So just imagine this inverted triangle here. I'm going to leave that blank, okay? We're not going to do anything with that. We're not going to put points here or anything else, okay? So this is a triangle here, here, and here. So I'm going to, again, do the same thing. So let's look at the top, okay? See this inverted triangle here? I'm going to leave that alone as well. See what I'm doing? So I'm going to put a point here, here, and here, and then here, 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 and here. And I'm going to do this similarly with this triangle and also this triangle, okay? So look what happens. Again, not exciting, right? I mean, not really that exciting. You don't really see much, okay? But you can see, again, just look at the top part. Here, here, and here, right? You see now the triangle in the middle is left over, right? So this one here I'm going to leave alone as well. Let's see, this one here I'm going to leave alone, and this one here I'm going to leave alone, okay? Let's do one more. Starting to see a little bit more, not much, right? But you can see these are open, 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 and open, right? Let's do it again. Now you can start seeing it, right? So again, see the hole here, hole here, hole here, and you can see this triangle is matched up here, is matched down here, which looks like the whole thing, right? That's the whole point. Look at the small part, gives you the view of the whole thing, okay? All right? Now, let's do it once more, because this could go on forever. Okay, actually, one more after this. Okay, you can see more spaces are open now, right? Okay, and we'll do it one more time. Okay? Okay, and this is called the Sierpinski triangle. Okay, now, I have a program that just calculates these and just did iterations and copied them in for you. But you can see, it's an amazing fractal. Okay, it's just a basic two-dimensional fractal. Here's a fractal 2.0. But again, the way I did it, it has zero area, infinite number of dots. Because there's no area, okay? Because it's just dots. I'm putting in points, okay? And it gives you this wonderful little thing, okay? Later, I'm going to show you Sierpinski's sponge, which is really interesting. A three-dimensional view of this, okay? So just to go back really quick, this goes from here, here. There it goes. Cool, right? Now, the way I did it, is that the only way to get a Sierpinski triangle? No. There's another way called cellular accommodation. Like this. Also Sierpinski triangle. See that? Really interesting. How do I do it? Well, this is another way you can do it, is by looking at cell patterns. Okay, so for example, you see these, I don't know if you guys can see them there or not. You have 1, 1, 1. So what we want to do is kind of like the game of life. You ever heard of the game of life? That's really where that comes from. So this really comes from Stephen Wolfram, okay, which is part of who actually created Mathematica. And you guys know Wolfram app on your iPhone. That's also Mathematica. And what he said was, this is one pattern. He says, if you have 1, 1, 1, it's like life, right? You've got 3 spots, these 3 beams are taking up too much resources. So what we're going to do is we're going to kill one off. Okay, we've got 0 here, right? 1 dies, okay? Then you got 1, 1, 0. Well, there's still too many, okay? So what we're going to do is 1's going to sort of pass away here. We got 0 down here. Then you got 1, 0, 1. Well, the middle space is open, so these guys are lonely. We're going to put 1 back in there. So we got 1 down here. 1, 0, 0, there's only 1 life, 2 deaths. We're going to have another, we're going to create 1, put 1. This is just flips of this one, same thing. This one, again, there's 1 here in the middle. We're going to go ahead and keep 1 because there's only 2, there's only 1 living, 2 are passed. And same thing here, there's 2 are passed, 1 is living, we're going to add 1. And of course, if no one's around, we need to add life. And this is just a simple pattern. You guys see this? It's a simple rules, right? These 8 rules, very simple, do you agree? But yet, when you apply these simple rules, and you go on the top here, you start off with 1, just the number 1, and apply these rules to every matrix going down, you end up with a Sierpinski triangle. Isn't that amazing? It's incredible, in my opinion. I mean, it's just simple rules, and like I said, it's chaos, right? It's like, I mean, it's amazing how you would actually get this, right? Simple rules gives you this, okay? Now, what about if I just made some random numbers across the top? Look what happens. Boom. It's like chaotic, right? So I just get some random numbers across the top and apply these rules, and look at these things. And you may say, it looks very random. It is, but you can look deeply and you can sort of see patterns. You can actually, like here, it looks like kind of a snake. I can see it over here somewhere. I saw it earlier. Yeah. I mean, you can see some patterns in this thing. It looks random, right? But it does gives you this beautiful kind of mosaic. Well, it's not really a mosaic, but gives you sort of a beautiful pattern. When this came out, I was like amazed. It's beautiful, right? I thought. And it's just using random numbers on the top, 0s and 1s, that's it. Okay? And applying these patterns to the next cell, and it creates this amazing looking pattern. Okay? And what I did next is I took a 1, a 1, and a 1. I filled the rest with 0s. Look what happens. This is actually, Sierpinski's triangle starts, but it splits, right? You see how it splits? It's symmetric. It's incredible. Symmetric. So, and it's really interesting. I can see sort of hearts in there. not really, but I mean, you can use your imagination. It's kind of like looking at the clouds. Oh, it looks like a dragon's head or something. You know, you can sort of imagine different things in here, but just basic cellular automaton, as they say. Okay, it's really interesting. This is just a taste of this subject. Okay, Stephen Wolfram has all kinds of rules, different new state for center rules. Okay. This one here, even in nature, look at this shell. Look at these kind of these inverted triangle patterns. Like we saw this earlier, right? This one, these inverted triangle patterns, kind of weird. It comes up in these shells. And this is, it's hard to see maybe up close, maybe back there you can sort of see some more patterns. But Wolfram uses different colors, so you can use, not just, black and white as I did, or orange and white. But this is following Rule 30. And again, sometimes you see these in nature, okay? And now, again, it's kind of like morphogenesis, okay? Perhaps simple things like this, like these rules, lead to more complex shapes, understand? So again, that's what I want to keep coming back to. Simple rules, when you iterate them, lead to seemingly, or could be, complex shapes, okay? Or complex systems. And that if you change one small thing, the outcome is completely different. So in other words, if you looked at both outcomes, you could not determine what the inputs are. Okay? It's just radically different. Okay? Radically different. Now, this is my Fern fractal. I like this one. I actually rendered this one. It's using a two-dimensional linear equation. This is like a line, but it's like a sort of like a two-dimensional kind of a transformation line. So you have this this matrix, multiply by some linear transformation, add some translation, and what you're going to do is you get these 4 different possibilities, and it depends on the probability. So 1% of the time it's going to use this one, 85% of the time it's going to use this one, 7% this one, and 7% that one. So it's just going to translate. What we're going to do is we're going to start off with a few basic points, and we're going to create a fern. Now, you guys know what ferns are? No, of course, maybe in the West, of course, we know what ferns are. Your grandmother had ferns growing in your place. But Garfield, Jaffe Mel, they like ferns, eats ferns, right? That plant. How do you say that in Chinese? Fern. Okay, maybe you don't know what a fern is. Okay. Anyway, you'll see what a fern is, and you can tell me what it is. But the fact is, what's great about a fern is like a tree. If you took a piece of the fern, right, you ripped it apart, and I took a photo of it and blew the photo up, I'd say, is this the whole fern leaf or is this a part of? And you probably cannot tell. It's like a fractal, okay? That's the whole point, self-similarity. Small part of the whole shows you the whole piece, okay? So watch what happens. I start off, not much, right? But you can sort of see the idea. The fern's going to tilt to the right, okay? Going to tilt to the right. You start seeing some things, it's sort of a shadow of it, okay? Shadow. But if I iterate it again, and you start seeing it, right? It's just a sort of a shadow. This is sort of like the main stem, right? And it's hard to see self-similarity at the moment. But if you look at this leaf, right? This kind of looks like the whole piece, right? Sort of, a little bit, right? If I do another iteration, one more. I got one more after this one. See, now you can see it quite more clearly, right? Look at this leaf right here. See this? If you took that and you tilted it this way, you would get the whole fern, yes? And it kind of tilts to the right. And you can adjust these, play with these numbers. You get some weird looking shapes, okay? But you see how it's self-similar? I mean, look at here. See that right there? Doesn't that look like the whole fern? Or here, maybe here. See? Looks like the whole fern. Looks like the whole fern. This little piece here looks like the whole part, right? Now I'll do it once more. This took a couple hours to render, by the way, my computer. It took a while, okay? But this is actually 19 numbers, iterations. That's it, 19 iterations. Not much, but it took a long time. And this is, actually there are pictures on the web that have used different colors, and it's really amazing. You can see like different shades of the colors and how they are placed. It looks pretty close to what a real fern looks like. So, oh, go ahead, Bob.
This was done with Mathematica, and you chose the probability, 1% for the first?
No, this is actually a set probability that you can,
okay.
yeah, this is not mine. These are, this is a common, you know, if you want to draw a fern, this is the numbers you use. But you can certainly play with these numbers and you get some ferns that tilt different ways and look a little different, yeah.
So if you change the probabilities and you run it through Mathematica, then you'll get actually different.
Yeah, yeah.
Sure.
Well, this is a pretty cool looking fern. So you guys know what this is in Chinese? Oh, Juliet? Juliet, okay. Yeah, these are pretty common, right? At least they used to be. I don't know anymore. But if you go, you know, in North America, if you go walking in the woods, you see ferns all the time. And ferns are one of the oldest plants I understand on living Earth. They're very, very old. So it's just a really neat kind of thing. Okay, we're getting done here. So I don't want to hold you up too much longer. Now, the Mandelbrot set. Now we're going to start getting some more exciting things. These are not mine. Okay, these are actually mathematical. There's from the Mathematica site. Okay, Wolfram, and this is a Mandelbrot set. Now, the Mandelbrot set that I made is pretty basic. Okay, it takes a lot of rendering, it takes a lot of time, but these are done with beautiful colors. And it's basically a quadratic recurrence relation. Z means complex numbers. Okay, basically we take the complex numbers and map them onto a two-dimensional plane. Because when you think about it, A plus BI can be represented as AB in a plane on some level, a basic level. And that's all we're doing. We're just putting it on a two-dimensional plane. Okay, for you math people. Now, here we are. This is the general what the whole bulb looks like. Okay, and I don't know if you guys can see it that well or not. It seems a little bit dark. It's clear on my screen. But again, I want to show you self-similarity. So this, for example, look at this little bulb here. So let's move up here. See how, if you can imagine the whole thing tilting this way, right? Well, this little bulb can be right here. Now look at the top. Look at the bulb. It's the whole piece. You see? Self-similar. It's over and over again. It's extremely complex, and you can zoom in, and as you zoom in, you see more and more of these things. You actually zoom in. It's like space is different. It's not, there's really size means nothing in these kind of spaces, okay? Because you can zoom right in, keep zooming in. If you have one that's deep enough, like numerically deep enough, you can actually zoom in and keep going in, and this will become really big. These Julia sets, or these things here, will actually expand, okay? And you'll see more. And you can't see this right here. Maybe you can't see it. Well, that's another bulb, okay? You'll see it again, okay? You keep seeing these over and over again, okay? These shapes keep coming up and up and up, okay? And these are just some other parts of the Mandelbrot set. Here's a bigger one. It's a little bit dark. It's so bright on my screen, but it's dark on you. But again, see this little bulb here? And it's like these little guys here. Little ones, little ones. It's like looking at a field, right? And these little bulbs along here. I mean, who knows? Maybe we're on the bulb right here. See? This big one, right? Could be right. We could be looking right here, right? So, where are you? I don't know. I mean, with a math package, you know your location. But if you're just caught in a fractal, I don't know. You wouldn't know where you are. That makes sense. If distance and time, well, not really necessarily time, but sort of like distance and placement mean anything. Okay, so you don't know really where you are. Okay, this is why it's just really cool. And it's just an example of a Mandelbrot set. And again, look at this equation. Simple equation. Not difficult. Understand? That's what I'm trying to impress upon you. It's just a simple thing that when you iterate over and over again, it creates complex, just beautiful patterns that are just amazing. Like you just can't believe that it can come out of that. Okay? And that's just not Mandelbrot. You even have three-dimensional stellar automata. Okay? Here, it starts out with something small and it grows. Okay? And when you start off something small, you get that thing. Okay? You don't know how, I mean, you don't know what they're going to expand like. Okay? You change some initial conditions here, this result will be, again, quite different. Very different. Okay? Okay, one last thing before we move on to that little film clip. This is my fractal trees. Okay? And so I created some trees a couple years ago using a math package. And this is not a tree, obviously, but these are just, I'm just showing you some of the cylinders. What I'm going to do is join cylinders together, okay? try to simulate trees. So I'm going to like simulate branches and trunks and so on, okay? And by using the idea of fractals, just some basic conditions, you know, the size, the length at which from the end where I join the other cylinder, okay, that's it. It's very simple initial conditions. And I iterate this over and over again, and I get these trees. I'm going to show you. I'm going to show you some evolution, okay, because the first part, trees turned out bad, okay? So here's just this is not a tree, this is just wood, pile of wood, okay? This is what happens when we cut the tree down, okay? But it just shows you how the cylinders connect. Okay, so the first tree, well, my first tree didn't turn out very well, okay? It looked like it grew up around Chernobyl, all right? I mean, you see, you know, they've got the stem, and the first branch really went out, and look, it's like leaning way over. It looks bad, right? But it's just a practice, okay? I was playing with the parameters. But you can see this tree is messed up. And it's three-dimensional, by the way. I don't have it here, but on my computer I can spin it for you if you want to see it, okay? But obviously it's just the first tree. It's a Chernobyl tree, okay? Next one, not bad, okay? I put some little leaves on the end, just put little dots. But, you know, this stick is supposed to be the trunk, and I just did some initial conditions, and it looks okay. It's not that great, okay? It's a little bit weird, okay? But it's just an example of just taking these cylinders and just basic conditions, joining from a certain part from the end with some variance, and joining the next cylinder, okay? One more. Oof. This tree kind of got, it's like a hedge, right? So I made it really small. I changed the parameters just a little bit, and I got this. So this was the first parameter. Okay, and this is the second one. So you can see I made the parameters different, and the tree completely different. Okay, next one. This is not bad. Looks a bit like a pine tree, right? But the problem with this tree is if you were to rotate it. I'm showing you the best side because if you rotate the tree, it's like flat, kind of like. It's not flat, but it's a bit flat, you know? What tree is like that, right? But it's just a trick. This is the best one right here. That looks pretty good, doesn't it? Not bad, you know? Looks kind of normal, you know? But it's just, I mean, does it really look like a tree? No, but it sort of looks like a tree, right? And I'm just using basic things, just cylinders, some basic initial conditions, where to put the next cylinder, and here I get something that looks like pretty close to a tree, okay? I mean, I could dress it up, I could put leaves in the end, you know, whatever. I could probably make it look pretty good, okay? So it's just, again, basic things lead to, when you iterate them, lead to complex, maybe unpredictable results, okay? Okay, now, we're going to finish up here. The last thing, remember I talked to you about the Sierpinski sponge? Remember we had the Sierpinski triangle I talked to you about a couple times? Now there's a sponge. This is really cool. So it's like a three-dimensional Sierpinski's triangle, but now we're doing it in a sponge. So you can see that they've taken out a big chunk of the face, and actually not just the face, the side, if you want to call it. They took out the middle, right? Did the same thing on the top and the side, and kept doing it over and over again. And you can't really see it here, but if you were to zoom in here, right, you would see the whole thing again, right? Okay, the closer, if you want to call it closer, the closer you move into the sponge, you see the sides, you see the whole thing again, right? And that's what a fractal is. Self-similar. You see a small part, you see the whole bit, okay? And this is like from Minecraft, kind of cool. But it's like if you were to, you know, if you were to build a building like this, right? It's kind of cool, right? It looks like something out of Star Trek or something. Maybe, I know what, the Borg? Maybe we can build a ship for the Borg, right? Right. But you know, again, it's just kind of cool. You can see inside it, right? It's like really wild, I think. And if you look, if you're standing inside it, it's really cool. Like a mine shaft, right? It's actually inside the thing. Okay, so you can actually see up, right? And it kind of cuts through. And again, it may be hard to see, but you can go through it here and here. And if you were to, again, actually, you don't even have to go there. Just look on the floor. You would see the whole thing again, right? In a small scale. Okay? So you can walk over here and you see the whole bit. Again, it's what's interesting about fractals. Okay? Okay, so three-dimensional fractals. I got a little video clip for you. I hope you can see it. What I want to do is this is a video that this guy did a three-dimensional fractal. Okay, it's a Mandelbrot set. It's off YouTube, so you can download these freely. And he put some music to it, which is really nice. And what's neat about it is that it took him 165 hours. 165 hours to render, okay, to create this thing. Okay, now this program he used is freely available. It's freeware to make these things. Okay, so I'm going to play it. It's just a few minutes long, and I hope you enjoy it. Here, I'm just going to, oh yeah, right here. Just one moment. Okay. Oh, what happened? Okay. And you can see that that was really only just a part of the whole fractal. You know, just a small part of the whole fractal. And if you took that video and you went into those walls, you'd see even more. So it's really incredible. It's amazing. Mathematics just leads to some beautiful things. It's just incredible. So anyway, I hope you enjoyed it. And that's my fractals. And I just hope you enjoyed the presentation. If you have any questions, I'll take some questions now. Take some questions? Anyone have any questions? Yes, Sean.
Would you say our universe is a fractal?
Oh boy.
Just say yes. Just say yes. You can't prove them wrong.
I don't know. It's just hard to say. It really is. I mean, I think fractals give us some understanding of things. I mean, if you look at a tree, is it exactly a fractal? No. I mean, is it completely self-similar? No. There are other things, but it just gives us, it helps us give us an understanding of how to make sense of complex, what was seemingly complex shapes, like, you know, mountains, rivers, and so on and so forth. So, you know, that's a very interesting. I mean, people say the universe is a hologram, so I don't really know, but I just think fractals are a way to help us describe complex phenomena. Yes, Bob.
Yeah, maybe I can comment on that question. There was a book called Gödel, Escher, and Bach. I don't know if you ever heard of that. It won the Pulitzer Prize, I think, in 1980 or something like that. It's very, really great book. Obviously, won the Pulitzer Prize, but it wasn't read very much. And Douglas Hofstadter, was that the guy who wrote that?
I don't know. Yeah.
He said that you can look at any system of chaos and you can see patterns in it. You can eventually see patterns. So if you look at the universe and you can eventually see patterns.
And that's really what it's about. Right. That's
recursion and iteration.
Yep. And that's what it's about. Exactly.
And I'm not a musician, although Mike is. Not many people know that. Mike's a musician, and he can tell you about the recursive relationships in music, for example, like Bach. How you listen.
I mean, you're right. I mean, if you think about it, a mountain is created, right? I mean, do we do iterations of simple things to create mountains? I mean, no, it's not how mountains are created. But I think it just can lead to mathematical models to help us explain or to help us make sense of these more complex shapes. Yes, John.
Why can't it be used for the stock exchange? As you said, it doesn't work.
I didn't say it didn't work. People are working.
Work very well.
Yes, but you're right. But people have been working on that for a long time.
And what's the big problem?
I don't know, actually. I haven't done much research in it. Haven't done much research into it, but maybe it's not just finding the right model. I don't know. It's more complex than, just like I was saying, just like with trees. I mean, if you look at a tree, is it a real, is it a fractal? Well, yeah, I mean, we can see fractal things in a tree, like the branches and so forth. But I mean, is it really truly a pure fractal? No, right? So I mean, I think the stock market, for example, it's more complicated than that. We just get a general idea. Yes, Sean.
So because you're saying the tree is just too complicated, we can know enough to get a general idea. If we had enough coordinates at the beginning, couldn't we predict exactly what it will look like?
You ready?
So
it's more than just that, I think.
Yeah.
See, with these models, I mean, you're putting in just initial conditions, and you're getting these what we call fractals, like the Mandelbrot set. You're putting in a basic thing, like you set a value for A, and you set a value for C. C is a translation, A is the value you multiply the Z n squared by. And just using those numbers, you get the Mandelbrot set. Okay. But as far as changing conditions to get something that we consider, I mean, it's possible. I don't know. I mean, it could be. But I mean, trying to find that and to create the tree outdoor here, I don't see how they've been able to do that. Or
eventually. Because you were messing
Perhaps.
around with the proofs and you made those trees. Couldn't you eventually get that down to a system where you could make exactly what you wanted?
Boy, if you could do that, you'd be... Because if you could do that, then I would say the stock market would be pretty... That would be That'd be like predictable.
Because it seems like if you can do that, then you can predict where everything came from just by looking at something we have now, and can't that let you predict the future?
Well, that's what mathematics is all trying to do. We're trying to predict, we want to try to predict future events by looking at past events. But there are other values in the systems that I think are just variables. You see, it's the assumption that we know everything about the system to develop that system. I mean, human life or just basic things. I mean, do we know everything about it that if we just have some model, we just put in the right variables, we're going to create the perfect thing? And I think, no, I mean, at least not right now. I mean, this is part of the problem with the 2008 crash. People rely too much on those mathematical models, weather models. I mean, otherwise we'd be able to predict weather really well. Is it just a matter of finding the right model? I don't know. I think it's more than just that. You see, I think sometimes it's easy for us to oversimplify. We look at maybe the system is this. We can handle it. If we iterate that, we will create the system. Well, I think it's hubris. I don't think we can actually do that.
Is that
because well, I'm just going to say because systems are far more complex, and there are variables that we just cannot sense and have effects that we don't understand. So for example, when a system gets very, very large, I mean, there are certain things that start interacting that we never realized that we were interacting for. So
by us interacting with that system, won't the system continue to expand and get more complicated? Then it'll turn into the Achilles tortoise thing where us chasing it, trying to simplify it, will always be longer.
That's interesting. Will it get more and more complex? Well, sometimes, some of the fractals, as you saw, if, for example, the mountain fractal, that triangle and how it became a mountain, well, yeah, it would become more and more, I guess, essentially complex. But just like, for example, the logistics model, I mean, it doesn't change, okay? Yeah, I mean, I think fractals, or the idea of good idea of fractals is, can we develop a system, mathematical model, that when we iterate that model, can that model help predict real life, something real life? And again, I would say, now John's of course the economist here, but I would say a lot of the problem in 2008, people relied a lot on mathematical models for these things, and it didn't work. We had a lot of problems. I think it's easy for humans. We can easily oversimplify things, make things too simplified, and where in fact systems, the axioms that we rely upon to develop, when we think of a system, we try to group things together, say, hey, this is what it is. But in fact, the reality is there's probably a lot more inputs into the system we can realize. And those also interact. The things that we don't know. I mean, it's really, mathematics is not about what we know, it's what we don't know. And that's what we have to think about. So we can only use systems or use mathematical models to a certain point, to a very limited range, in my opinion. So yeah, it's fascinating.
But in physics, if you're given the initial conditions of a particle, the initial momentum, energy, position, so on and so forth, you can predict at any time in the future where that particle will be. And you can do the same thing for 2 particles, and you can do the same thing for 3 particles. The problem is that when you get down to large numbers of particles, even if you do know the interaction, it's just too much.
It creates chaos. Yeah, that's right. It's more particles enter the system. It creates chaos.
It creates singularity.
It's kind of analogous.
Perturbation theory.
It's kind of analogous to people, right? Sorry guys, I'm almost finished here. So it's kind of analogous to people. You have one person, and you have a couple people, and then a small group of people. The group dynamic is, we're familiar with that. But when you start getting crowds of people, you see how it changes? How people start just acting, it's almost fluid. I mean, you see, when you start getting huge groups, we start acting differently. And we're not individually acting any different than ourselves, right? But as a group, you look at the whole picture, the crowd acts differently, okay? And that's really what it's saying. So, I mean, it's things that if I got to know one person, if I've never seen a crowd before, right? A big crowd. Could I predict by knowing people, a few people, what a crowd will act like? No, probably not. Okay, that's chaotic. The way we interact with things, the iterations, okay, creates a chaotic system. It's very interesting. Any more questions? Okay, thank you very much.
So that'll be an IQ, are you gonna send this?